Hello?
Hello, Alan.
Oh, give me a second. My computer audio is low. Hello?
Hello there.
There we go. How are you?
All good. Waiting for Yusuf.
Mhm. How many slides do we have today?
Yusuf, hello.
Hi, how are you?
Oh, hi. I'm great. How are you doing?
I'm good.
How is the home assignment?
It's good. I'm almost done it.
Yeah, it's easy.
Yeah, it was pretty easy.
Make sure to make a PDF file and send it to me once you're done.
Yeah, okay.
How about you, Alan?
Good.
Do you have any questions about your home assignment?
I don't know. I don't have any questions.
Not right now.
Okay. So today we are going to continue. Oh, just give me a second. So we're going to continue study properties of function in terms of maximum and minimum of a given function at a range. We're also going to take a look into methods of solving some kind of real life problems related to optimization. Optimization, you can understand it as choice of configuration that complies with requirements at greatest scale. Do you get it? So,
Yeah.
well, what are we trying to reach when we are solving optimization problem, guys? What do you think?
Don't have an answer.
So I would call it optimization problems is basically when we ask some concept of calculus to help us optimize our production, let's say. Because knowing how we can study the function can give us answers to some interesting questions that we're going to take a look into today. For example, when you're designing even a simple metal box, you have to apply calculus to find the best solution. If you have some volume considerations. But you're going to take a look into it a bit later. So as outcomes of today's class, we're going to practice new methods of finding the absolute extrema of the function. Because remember, in the last class, we finished at the point where we found the full square, the complete square of a function, and compared the result with finding values of a derivative when it's equivalent to 0. So if we would like to discover some function, let's say it was quadratic function like this, one method you knew before is to find a complete square of this function, right? To find the vertex, thus find the extreme value of a function. Do you recall that? Minus b divided by 2a. Remember
Oh, yeah,
this?
yeah.
Now popping up, right? But now we don't need to use this old school technique, because now we studied that this extreme value also related to the derivative in such way that derivative at this specific point is equal to 0. So we can find this x value at first place. Let's say x, in this case, minimum. Would be a solution for equation the f prime of x equals 0. So basically, let's say we're given with some quadratic function like x squared plus x plus 1, okay? And this is parabola, right? And it's positive parabola because we see coefficient in front of x is positive. It's looking upwards. And to find this point where function changes its direction and thus being an maximum extrema of the function. Did you get this concept?
Yeah, I think.
Let's say if initial function f of x is equal to x squared plus x plus 1. Now we find a derivative of this. And it would be 2x plus 1. Am I correct? Now we just need to evaluate when this function equal to 0. As soon as derivative is just a linear function, there is only one solution. X equals minus 1 divided by 2. So this would be the coordinate of this point. This would be x of this point. So now to find coordinate of this point relative to the initial function, which is polynomial function that gives us this parabola, we're just simply going to substitute x here for this value of x, -1/2. Thus, we're gonna get when x equals -1/2, function would be -1/2 squared plus -1/2 plus 1. And we just need to evaluate this. Yusuf, can you help me?
Oh, yeah. This one would be 0.75.
Sorry.
0.75.
Yeah, is that the final answer?
Yeah, I think. Wait.
No, you're right.
Yeah,
How much?
0.75.
0.75. So now we obtained the y coordinate of this function, right? Of this point of the function where it reaches its minimum value.
Yeah.
Am I right? Am I not?
You're right.
I mean, so now we can confidently say that this point would have coordinate negative 0.5 for x, right? And 0.75 for y.
Mhm.
Instead of finding the complete square, we just apply derivative properties. And you had this at home assignment. I just would like to clarify it with you. You got this, guys?
Yeah.
Okay. Then let's proceed to the next slide. Here's an algorithm, and I would like you to read it. And once you read it, I would like to ask you one question. If a function f of x has a derivative at every point in the interval, why this is here? How do you think? Take I don't answer right away because it's not easy.
What's the question?
Why this is part of statement. You see, this statement is true only if a function f of x has derivative at every point in the interval. So we say that function should be differentiable at the whole range, not just at this point, but at the whole range on the graph. You see, basically, if we have some function, I don't care how it looks like, let's say like this, and we say we study it at a range from x equals to a to b. This would be our range. And we say that this function should also be differentiable at whole range. We shouldn't have any problem here, like empty point or break like we seen before. Remember when value jumps? If something like this happens, we cannot apply this rule.
Mhm.
Because do you understand why? Because it's definition of a limit. And limit is basically a parent of a derivative.
Yeah.
Yeah.
Well,
Remember, no, do you remember this definition of limit? And
yeah, but in the original graph, there was no limit in it. You had
what?
whenever you drew that graph, it was just like that.
Yeah, this is just another example. My graph could look like this. If it looks like this, I cannot use this rule to find extrema. That's the reason that my graph should look like this. It should be continuous. It should be differentiable at every point on the interval
Mhm.
from A to B.
Mhm.
And definition of a function being differentiable is that limit exists at every point at the interval, right? And limit from both sides reaches the same value. Do you remember we studied limit, for example, a positive or a negative from left or right to this point, and if this limit is the same from left and right, like L1 equals L2,
Mhm.
then limit exists, thus derivative exists.
Mhm.
So now we say that if derivative exists, we can apply this algorithm to find minimum and maximum values.
Okay.
So if if it's easy with you, can you give me a quick answer for this question?
Yeah.
Extreme values at the interval.
Mhm.
Yeah, take a few minutes and just prepare the answer. And whoever wishes to answer gonna get like extra mark for this class. Extra +1. Just explain the whole solution. Okay?
Okay.
Take a minute.
Okay, I think I got it. I think I got it.
You think you got it?
Yeah.
So write it down on the desk.
Okay.
I think I got it too.
Can you comment on your writing, please?
Sorry?
Okay, Alan, can you comment on your writing?
Can I what?
Comment your writing.
What does that mean?
Explain
Oh,
your line of thoughts. How
Right.
are you solving? What are you doing?
So first I just wrote down the equation and then I found the derivative of it. So I'm just gonna write the derivative because we know how to find it already. And then I took um so what I did was I took this value here and I plugged it in. Was that wrong? Hmm?
Can you hear me?
No, I didn't hear it.
Can you hear me now? So
I took that value and I plugged it in, but I don't think that's right. You can't solve it that way. 'Cause it's not-
let's think. Let's remember the algorithm. Do you know the algorithm? It's right here.
I didn't write it down.
But you have it in your
Yeah.
reading
Okay.
material.
So it's equals to 0.
If we have for the
So
second
first
step,
thing, see, let's check if it's differentiable. Yes, we don't see any problem at the interval from -1 to 5, right? Next step, we'd find the derivative. You did it right. Okay, you did it right. Now you gotta say that derivative equals 0. Let me add my mark here.
So then,
You gotta say this equals 0. And next step, evaluate for x.
okay, here, I got it. And you would, where would you go from here then? Oh, wait. Would I be able to factor out an x from the equation? Would that?
What?
Well, I got to this part, and then
Now you need to find what x is equal to.
well, there's an x on both sides.
But you made it so x is on both sides. If you look a step back, you had minus 6x squared plus 18x equals 0.
So
Now
like,
I would just factorize it. I would factorize x and
Yeah.
minus 6. I would say minus 6x
okay. And
times x plus 3, minus actually, minus 3 equals 0. Now I can state that x1 equals 0 and x2 equals 3. These two values when this function takes value 0. Now I take a look if my points are within the given interval.
Mhm.
-1 to 5, 0, 3. Yes, it's absolutely perfect. Now I would sketch my graph. Not so hard, real quick. So we have some kind of quadratic function. So I believe it's gonna be, let me cheat actually, because we have it here, yeah. You see how it's gonna look like?
Oh, okay.
So, because, and you know, it's not gonna be parabola because it's third power, you see? And third power, it is, it has a bit different view. Pattern, different pattern.
Okay.
So, and I select range from -1 to 5. And my points 0 and 3 are gonna be exactly here. You see it? At the bottom and on the top. And in both cases, function changes direction after reaching this point, like this break-even point. You see that?
Mm.
So now the next step to evaluate, we ask find the extreme values of the function. Now what you gotta do is to evaluate, because you know that before this point 0, if value of the derivative, oh sorry, if value of a function before here is greater than this one, it means we were going down. And if value here is greater than here, it means we were going up. And as well, same property for here. Thus, you can see that among these points, you're gonna get the biggest value and you're gonna get a smallest value of a function. So f of x basically min and f of x max. And these values are somewhere among This four values for x, which are x1 would be -1, x2 would be 0, x3 would be 3, and x4 would be 5. And now you substitute x in your initial formula for one of these values and calculate the value of a function. Just solve it for x, basically. And eventually, you see here we have 4 different values. Let me shrink it a little bit. So you see, when we substitute x for our 4 values of x, look here. Do you see this? We get 4 different outputs,
Mm-hmm.
4 different values of a function. Can you analyze these values of a function for me, Alan?
Yeah. So f of 3 we know is the greatest, and then f of 5 we could see it's the smallest. So that would be your minimum. Your maximum would be 31.
Also, what I can see here, that from -1 to 0, value of a function decreases. Then from 0 to 3, it grows up. Then from 3 to 5, it goes down again. So it means that if here I'm going down, it means before it doesn't matter where I was before, because we have limited interval -1 and 5. So you basically cut the function off. You look at the values on the edges, and you find extreme values inside. But take a notice that even though 0 was an extreme value, right? Do you see that?
Yeah.
This was one of the values when function turns, when the derivative turns into 0, when we change direction. Even though this was the minimum point here, it wasn't the minimum value on the whole interval of a function, you see? We reached even lower. I hope it's clear to you, and we can move on, guys. What do you think?
Yeah.
I'm just writing it down right now. Give me a second. So the final answer would be the maximum value is f of 3 and the minimum value is f of 5.
Yes, exactly. And right, what is the minimum and maximum values?
So what was the point of calculating the zeros then? What was the point of calculating the zeros?
Because we studied where this function reaches its minimum or maximum values within the range.
Okay.
Because and we describe those minimum and maximum as points where a function changes its direction. Because if the function was decreasing before that, it means this point was the lowest point that function
Yeah.
get to, right? If we were growing up and then we changed direction again, it means it was the maximum value we reached.
Yeah.
And you see one of these zeros which is x equals to 3, is the maximum of a function.
Yeah, I see that. Okay, I got it. Okay.
So, who's brave enough to read this?
The amount of current in amperes, A, is an electrical system. It is given by the function C of t equals negative t cubed plus t squared plus 21t, where t is the time in seconds and 0 is less than or greater, less than or equal to t, and t is less than equal to 5. Determine the times at which the current is at its maximum and minimum, and determine the amount of current in the system at these times.
No, great. So, so let's define right away what we get. So C of t is the function of current in the circuit, right? Depending on time. Am I correct?
Mhm.
So now we would like to know, and we also have a range for t from 0 to 5. So t belongs to the range from 0 to 5, including, right? Not a round brackets, but square brackets,
Mhm.
because we include those points. Now we gotta, if we're asked to determine at which the current is at its maximum and minimum, we just simply refer to a property that C prime of t, or in other words, if we use the our, I forgot the name of this notation, guys. Can you help me out?
Which one?
If we write it as differential, like d over dt,
Um,
Leibniz
they-
notation, dc, we can write it as a dc over dt. So derivative of function of current by time, and only no square here because they're taking derivative once, would be a derivative of, it would be d over dt of negative t to the third power plus t squared plus 21t. And now we just need to differentiate it, obviously. And take a look that this is, for example, function describing a physical or real world phenomenon like current, right? And notice that this function is differentiable at the whole range, at the
Mhm.
whole interval. We don't have problem in this function. And mostly physical formulas that are describing real world situation, they shouldn't have this problematic regions like when you have infinity or something like that.
Oh, wait, can you explain it again? I didn't really understand.
So basically it's a remarkable phenomenon that real world uh, the formulas that are describing real world physics like friction, current, capacity, resistance, etc. They usually don't, they're differentiable at whole interval.
Oh, okay.
Mhm.
So now let's get back to the solution. We need to find the derivative. You can see it here. Let's not write it second time, right? Guys, do you follow me?
Yep.
Let's get in tempo. So if we set this equal to 0 and we evaluate it, how would you do it, guys? Don't look here, it's cheating.
You set it equal to 0, then you would do the, well, I did the product sum rule, so I found, well, this is like the method I learned in my school. I don't think I showed you. You multiply these numbers together.
Yeah, you showed me this.
Take
You multiply and you add up.
the B term. So it's negative 63, and then sum is 2. So you find two numbers that equal negative 63 and 2. So I think it's 9 times 7. Yeah. It'll be negative 7 and 9, I think. Yeah. So then you'd have negative 7 and 9. And then you'd go back to the equation, and then you'd have negative 3. 0 equals negative 3t, subtract 7, and then you'd have negative 3t plus 9. Then you could factor that down to 3t plus 7 and t subtract 3. There we go.
But eventually you got the same result as here,
Yeah.
right?
Oh, I didn't write it down now. I was writing on my paper.
So what is your final answer?
It's exactly what I have down here.
Yusuf, do you have problem with this method?
No, I think I got it. Like the method he explained.
Like you also should know it.
Yeah, yeah.
So beautiful.
So then
So
the second part, we have to determine the amount of current in the system. So we just plug in the T back into the equation,
yes,
and that's how we get that answer.
can you tell me the answer?
Of course. A second, just to calculate it. Okay. It'll be negative. Plus 21 times 3. Negative 56.26
What, that's amount of current?
for T, this one.
Which one? For negative time?
Yeah.
Negative time. Doesn't that sound weird to you?
Oh, you can't have negative time, yeah. So you can't do that one.
And also, what range of your time is set in the
Yeah, it
problem?
doesn't follow the range either because it's negative.
No, range literally says from 0 to 5. You're not interested in any other values that are outside of this range.
Yeah. Then it'd be only 3, so that one you could cross out. Okay, let me just do the other one then. So 3 negative cube plus 3 squared plus 21 times 3. 45. Final answer.
What is 45?
Amperes. In the current. In
No,
the
no, no. What is that minimum, maximum?
oh, okay, let me
And what is the value at point of time 5
yeah,
and
let
0?
me calculate those.
So at 0, C of t when t equals 0 is equals to 0. C of t when t equals 3, it equals to 6 plus 7 is 13. It equals 0 again, right? No, its derivative equals 0. But then the amount of current equals to 27, negative 27 plus 9.
Yeah, it's the maximum.
Negative 27 plus 9 is
And the minimum is
18.
0.
Negative 18 plus 63. Negative 18 plus 63. How much is that? It's 45. Am I correct?
What was your answer?
So this is at moment of time 3, and moment of time 5, it would be
That'll be 5.
answer is 5.
For f of 5 for c of 5 is 5.
So negative 125 plus 25 plus
105.
150.
105.
Oh yeah, true.
So that would equal 5. So
Yeah,
the maximum is c of 3 at
yeah.
25. And the minimum is c0 at 0.
So yeah, and if you sketch the graph, you would see that it would pass through the big start of the coordinate system, right? 0, 0, C0, 0. Then C3, let's say, and be C45. C of t, 45, and 3, and 5, it would be here. And we know that at point of time 3, it changes direction, right? So if after 3 and 5 we're getting here, it means we were going up, then we changed direction and we went down. And this was maximum, the top of our graph.
Mhm.
And we don't care how this function looks beside this interval from 0 to 5.
Mhm.
So the final answer would be minimum was at point 0 and the maximum was at point 3. And respectively at point 0 it was 0, at point 3 it was 45. Great. Can I clean the desk?
Yeah.
So what is the time right now?
45.
7:45?
Yeah.
Let's take a look at one more example and then let's make a break. So here, guys, when the method is allowed, remember I said that the function is supposed to be differentiable at the whole range. So take a look at these following functions and tell me whether we can or cannot use the method we just applied to the function with following examples. And state me the reasoning. Why can't we apply it? Or can we?
Uh, For D, I don't think we can
Why?
because there is a asymptote. Or like X cannot equal 3 at D. And that's their range,
Actually, x cannot equal -3.
-3. Oh, okay.
So no issue with that one.
Oh, for B, X cannot equal 2. And that's in a range.
So Yusuf, what about B? Can we use the method or cannot we?
Uh, I'm not sure if we can or cannot.
Why? But we just discovered that we are using the algorithm that is based on existence of the derivative, right?
Yeah,
And we know that derivative exists if function is differentiable at whole interval of the function.
yeah,
So we remember that function is differentiable if we don't have any weird patterns, we don't have jumps, we can draw the curve a single line without taking the pen off the paper, right?
yeah,
And problems like function traveling to infinity are also not allowing us to differentiate the function, right?
yeah,
So, and we know that for this method to use, functions should be differentiable. Now we take a look at the A, B, C, D, and tell me, does any one of this function is not differentiable at the range that is stated? Can we differentiate these functions at the suggested interval?
And C, I don't know, you could do it either.
C doesn't work, right?
B doesn't work too.
What about A and D?
They work.
Perfect.
Yeah,
I agree with you guys. And why C doesn't work?
If you factor out if you simplify the denominator, you'd get X X subtract 2 and X plus 2. So then you can't have a plus or minus 2 because that would be an asymptote, or that would not be defined. And in your limit, you have a 0 to 5. So 2 cannot be differentiable.
Yep, exactly.
Do we solve them, or are we just writing down that they can't?
Now you found that B and C are solvable. Oh wait, A and D are solvable and B and C are not. So apply this method to A
Okay.
and that's it. And we make a break 10 minutes from now.
Okay.
okay.
Here's the conclusion algorithm. Maybe you would like to screenshot it for yourself.
Oh, yeah.
Are we not solving the practice questions now?
Pardon?
Are we not solving those questions now?
This?
Or are we doing that?
Yeah. I just here's an algorithm. If you get lost, I'm just offering you to screenshot it now, then I switch back and you can solve it.
Okay.
You got it?
Yeah.
So just solve A and that's it. We're gonna do it here. Guys, how are you doing?
Good.
Are you catching up with me?
Yeah.
Or am I too fast?
No, actually, I'm right where you are right now.
Mhm.
So I got wait, I can't be right. Give me a second, maybe I calculated it wrong. Okay. So I got two maximum values. Or like two values that hit the top. And one minimum.
Here it is what I got. Negative 230 over 27. And so this is for 10-3.
Yeah, I got the same thing.
So previously we found that at point 0 and 10/3, we change our direction and we see that from -5 to 0, we were growing. Then we went down again when we changed direction. Makes sense. And now supposedly we're gonna go up again. And we just need to find out how high are we gonna get. If we substitute 5 into here, it's gonna be 125 minus 125 plus 10, right? So we're gonna get 10 again. So eventually -5 was the lowest point, and at point 0 and 5 we have same value. Right?
Mm.
So we have three one minimum and two maximum values. And they're interchangeable between each other, so they're both equal.
Mhm.
Okay, let's make a break. 10 minutes and get back to the second part of the class.
Okay.
Can I clean the desk?
Yeah.
Perfect. Here is optimization problem. Please start reading and I'm gonna get back to you in 10 minutes.
Okay.
I'm already back, guys.
Hi.
Hi. Waiting for Alan. Have you read this, Yusuf?
No, I didn't.
Please read it now.
Okay.
Okay, I'm back.
Hello, Alan. Have you read this?
No, I was
Please read it now.
yeah.
So any questions so far?
No.
So it's these are just finding the best possible, let's say if it's a cost problem, the best possible cost.
Yeah, the optimal, let's say, cost. Yeah.
Okay.
Optimal means great required, for example, cost of a product to a margin value, for example.
Okay.
And you know, you're gonna see why we really love limitations, because here it's literally says that when we are just asked to make it tables and chairs, it's not clear enough. But when we got some limitations, for example, using this amount of material, spending that much money, we are giving it more input into our formula, right? So we are restricting possible number of outcomes by applying limitations. Like in the previous example, the interval of the function.
Mhm.
You see here, interval is actually one of the limitations when we limit or restrict the function to a specific range to study the function within this range. Is it clear?
Yeah.
So here, let's understand it on practice. Here's example number 1. And we're going to talk about simple problem involving optimal area. So farmer has 800 meters of fencing and wishes to enclose a rectangular field. So we would like to make a border, like, right?
Mhm.
We have 800 meters of fencing. So it means in line, we have 800 meters. And we would like to enclose rectangular field. So we would like to use this 800 meter to make a rectangle. So split 800 meters in 2 A's and 2 B's, for example. Right? Makes
Mhm.
sense?
Yeah.
2 A's, it's 2 lengths, and 2 B's is 2 widths. Or in this case, this side is denoted as X. And one side of the field is against a country road that is already fenced. So the farmer needs to fence only the remaining 3 sides, you see, of the field. The farmer wants to enclose the maximum possible area and to use all the fencing. How does the farmer determine the dimensions to achieve the goal? So, solution. The farmer can achieve this goal by determining a function that describes the area that we are going to enclose, right? And the amount of fencing used should be 800. So what is the formula of this area, of this rectangle area? Guys, any ideas?
No.
Wait, so what did you ask?
So if we know that our total amount of fence that we can use is 800,
Yep.
right? It means that total perimeter of this rectangle is 800.
Oh, so what are the side lengths? You asked?
So we suggest, no, I asked how to express the function of the area.
Oh.
So function of this area would be width times length, right?
Mm-hmm.
Am I right? Area of a rectangle.
Yeah, length times width.
So if we denote width as x, unknown quantity, right?
Mm-hmm.
Now we can substitute this formula in the following way. Area of a rectangle depending on x would be as x width times the length. And how can we express the length?
L.
But we can have only one variable in a function to be accurate, right? We need to express length in terms of what it's called in terms of x. So if we say that we use 800 fence for the 3 sides, right? It's not the whole perimeter of a rectangle. It's
Mhm.
only the 3 sides taking 800 meters, right? Because this wall is already built by the road. We would
Mhm.
like to use 800 only for the 3 sides. So if one side equals x, then area would be x times length. And if we know the total length of these 3 sides is 800, it means that this length would be 800, subtract 2x, these 2 walls, right? Right here. And we have only one wall left. So it would be 800 minus 2x. Make
Okay.
sense?
Yep.
Yusuf,
Yeah.
you got it?
Yeah.
Why 800 minus 2x?
Because you have 800 meters of material. So, and then you'd subtract that by 2 because there's 2 lengths, and then x because you have 2 widths, so you can't take up all 800 material or meters on the length. You have to subtract that by 2 widths as well.
Because we spend 800 on 2 widths and 1 length, right?
Mhm.
So
Oh, sorry, yeah, one length. Oh, because yeah, one side's blocked. I didn't read the question because one side's blocked off. Yeah.
one side is already done for us.
Mhm.
So 800 minus 2x, cross out these 2 walls and we get only length left. So width times length is the area function. And we simply have quadratic function a of x equals 800x minus 2x squared, right? Guys,
Yeah. Oh, wait, can you repeat that again?
So now we know the formula for the area that we cover with our fence, right? It's gonna be 800 times x subtract 2x squared, because this was the previous step and we opened the brackets. This is what you see here.
Mm-hmm.
Do you understand it?
Yeah,
Why this function of what is x standing for, Yusuf?
X stands for
Width.
no, the height.
Why height? Because we're covering the area on the field.
Yeah.
Where we're not covering area on the field upwards. It's surface of a ground. Here's the road passing. It's totally width and length
Oh, okay.
because it's width of the field. While height is, if you wish, it would be z direction, right? But we are in two-dimensional because we are solving problem of an area, right? Area is 2 dimensions, or meters squared, or centimeters squared. That's the unit of an area, right?
Mm-hmm.
When we're gonna solve problems about volume, then we're gonna talk about three-dimensional objects, 3D objects. Now we talk about 2D. So guys, let's move on. Is this clear or not? I can't understand you.
Yeah.
Yeah, it's clear.
So remember the previous step, we determined the limits, basically the interval of this function. In this case, we basically can take x anywhere between 0 and 400. Do you understand why? Because, for example, if x equals not 400, but close to 400, not 400 because we can have length equals 0,
Mm-hmm.
okay?
Oh, wait, the domain of the function is that. Did they give us that, or did we solve for that?
Sorry.
For that domain they gave us? Did they?
It's not what they give us, it's what you should come up with.
Yeah, it's just okay.
We have 800 meters of fencing, right? And we have two axes. Whites here and whites here. And length depends on the whites we choose, right? And whites could be anywhere from 0 to 400. For example, if we spend 399 on one whites and 399 on the second one, we're gonna have 2 meters left for length, right?
Hmm.
Guys,
Yeah.
if we have 400, it means we have 0 left for length.
Mm-hmm.
As well as the opposite side. If we have 0 for whites, it means we are not covering any area.
Can I ask why we did this part here?
Which part? Because we didn't have any formula before this step.
Okay.
Because remember, initially what you need to do when somebody asks you an optimization problem, you need to express the problem in terms of a function,
Right.
to express it in mathematical logics and mathematical analysis. And here we were asked to evaluate the amount of material, to restrict some area using the fence.
Okay.
And we need to simplify it. What is this problem about? This problem is about area, right?
Mhm.
Area that we cover. So we write down How we define this area? It's going to be x, the width of this area, times the length. The
Yeah,
length, for the
I-
length, we're going to use all the remaining material that we didn't use for the width.
I understand that part. So to find this, we just took the x value here and then the x value here. And that's how we found that domain.
Basically, domain is going to be a solution
Yeah.
for this equals 0. So,
Is that
and we shouldn't have 0 area. You understand it?
so? Is
Because
that
area cannot be 0. If area equals 0, it means we are not in 2D. We are in one dimension. We have just a line. Line has no area.
is
But
it important to find out the domain?
yes, it's super important, because otherwise you cannot find maximum or minimum of the function. Because if you just try to test it out, go ahead, and you're gonna eventually find out that this quadratic function, which is basically downwards parabola, is gonna has it maximum, but you cannot truly say, because you're not limited. If you When you're limited, you have one value here and here to test, but when you have no limits in your range, you would have to test all the values here and lower and farther, and you can go for eternity. Because in fact, if you keep increasing x here, eventually you're gonna get to the negative infinity.
Mhm.
Am I correct?
Mhm. Yep.
And if you go into negative direction, also you're gonna get to the negative infinity. But once you apply these limitations, this negative infinity doesn't make sense to us, because only in this range, and you're gonna see it, from 0 to 400, area would be positive. Any farther you go, you're gonna see that area takes negatives value. If you take x equals 500 here, so 800 minus 1000 would be negative 200, right?
Mhm.
And as a result, even though x is positive, but positive
Oh,
times negative
Yeah, I
gives
got
us negative area. How
Yeah.
is that possible? That's impossible. That's why we have this range.
I understand this.
In another case, if we're not to asked about the area or some particular example, just in general, we were given with this equation, we would have no reason to apply this limitations. Here it clearly says, follow this, since the amount of fencing is 800 meters.
Mhm.
And also another thing, we simply cannot use 1000 meters for 2 wides, because we don't have that much fencing.
Mhm.
So it's out of the range. Did you get it?
Yeah.
Yeah.
So now next step would be to find the derivative of the area function, say it's equals to 0, and find solutions. And here we can see that only solution is equals to 200. So this top point of a function would be at x equals 200.
Mhm.
So we can say that optimal. Oh, and now we need to substitute this 200 to initial equation, and let's see, it's gonna be 800 subtract 400 equals 400 times 200, and 400 times 200 is a lot. It's 8,000, 80,000, isn't it? It's 80,000 square meters. Guys,
Yeah.
So this would be the maximum. And if you substitute two other solutions, 0 and 400, you don't actually need to substitute them, because you see they do not actually in the interval, they're not included, so you don't need to check those values.
Or
And another thing, if you take a look here, you can say this is upside down parabola. So anywhere outside from this point, it's gonna take lower values than in this point, right? So we know that this is the maximum of the parabola. If we would have another parabola like upward looking, we would know that this point would be the minimum of the function. Make sense,
Yeah.
Alan?
yeah, makes sense.
So what would be the answer? What is the optimal solution for the whites of this box?
The length would be 400 and the width would be 200 meters.
Okay.
Can you explain why? Or
You
self-explanatory?
it was pretty confident, but what gives you right to say that this is the maximum value? Why can you say that?
Which one's the max? 80,000?
X equals 20 to 200 and Y equals 80,000.
Well, I did it differently at the end. I
How?
didn't. So whenever I calculated x equals 200, I just kind of plugged it in. We know that the perimeter is 2 width plus length. So 2 times width plus length. So you just kind of plug in that and get 800. You're 200 and 400. Why use? I just used common sense at the end, really. I didn't do it algebraically.
You got so what you gotta do, you found the value of x at this point, right? At maximum of the function. Now you substitute the function that you were studying, and in this case you were studying function of the area. Look right here, right? Do you see that?
Mhm.
You were studying this function. So you substitute x equals 200 here. And once you evaluate it for x equals 200,
Mhm.
you're gonna get the area, right?
Yeah.
And if you were asked about the length, you would just simply say that length equals 800 minus 2x.
Oh, I solved question B. What is the dimensions of the? I didn't solve question A. Sorry, I was talking about question B.
What question A or B you're talking about?
In the question, it says, the farmer wants to enclose the possible area. That one, that's what you're asking. I was reading this question here. Or it's not even writing. How does the farmer determine the dimension of the?
Okay.
That's what I was.
Okay.
So for the first one, it's 80,000. That's the answer.
And how you obtain this answer?
You plug in the 200 back into the derivative formula.
No.
Or the original formula, sorry.
For what?
Area.
Great.
And for the second question,
How to find the dimensions?
you could use common sense. Can you use common sense for the original question?
No, you would say
Oh, you plug it into the
So-
length formula. You find the 400 and then
because it's not a common sense. It's still mathematical outcome. If you have 800 total, and you know that you spend X on one side and you spend X on the other side, it means you spend 2X in total. So the remaining one would be 800 minus 2X. It's
Mhm,
mathematics, it's not just common sense.
mhm.
So yeah, but you're right. You can say that you reach this solution by common sense, but you should be able to write it on the paper like this, 800 minus 2X, and you should be able to explain why. Because here we see, basically we use this formula to form area equation. You see that? We
Yeah.
have here width, which is X, times length, which is 800 minus 2X. So it's important to understand why we have such formula.
Okay.
Is it clear, guys? Did you copy it into your
And
textbook, copybooks?
area is measured in meters squared, right?
Yes,
Yeah, I got it.
Yusuf.
Yeah, I got it too.
Perfect. And let's take a look at one more example and we're gonna call it a day. So here's the solution they suggest. Do you see this?
Yeah.
At a equals 0, at x equals 0, we get 0 area. That's what I'm saying. When your whites equals 0, you don't have any area. You have just straight line.
Yeah.
And as well as if your whites takes all the 400 for one side and 400 for the other side.
Yeah.
Function turns into 0. Here's the volume problem. So a piece of sheet metal 60 centimeters by 30 centimeters is to be used to make a rectangular box with an open top. So it means if I were to sketch it, I would get rectangle block with an open top. So it means I have no material on top, right? This one is opened. A piece of sheet metal 60 centimeters by 30 centimeters. We have it. To be used to make a rectangular box with an open top, determine the dimensions that will give the box with the largest volume. Okay. So basically, dimensions that we have is going to be the let's take a look. How would you make a box out of rectangular sheet metal?
Length times width times height.
Not exactly.
Base.
Because remember, how would you fold a birthday present? If you're wrapping a birthday present, you always have excessive material on the corner, right?
Oh,
So to make a box, you gotta make a cutouts on the edges,
yeah.
and when you make a band on the material, you're gonna get nice and perpendicular walls, right?
Yeah.
So you gotta remove some material here, some material here, same for here, and from all the sides, you see? So you gotta remove X here and X here from the widths. So the width of the part, if it was initially 30, you see 60 by 30. So this is length. So this side would be length subtract 2 x's. You see it?
Yeah, I
And
learned this.
this would be width subtract 2 x's.
I remember learning this stuff in school, advanced functions.
Great, so it wouldn't be hard for you. And what is x here? It's not just a random value that we're cutting out.
Height.
It's gonna be a height of our box, exactly, because once we turn this wall upward, this turns into the height of a box. So now we have all the 3 dimensions that we need. The height would be x, the length would be 60 subtract 2x, and the width would be 30 subtract 2x, right?
Mhm.
Now, these 3 dimensions all together should give us volume of the box. And one more thing, we need to determine the range of this function, the interval that is suitable for it. So first of all, what we can say about dimensions in this case, they should be positive because we're talking about physical object, wall of a box, and wall of a box should be positive, right?
Mm.
So let's see, this function would be positive when x is less than 15. This would be positive when x is, this one is positive when x is less than 30, right? Guys,
Yeah, I got it.
Yeah.
less than 30, and this is positive when x is less than 15.
Yeah.
But we need to find the range. So even if this is x is less than 30, it doesn't mean we can take x equals 25, because if x equals 25, this would turn into negative widths, and we cannot allow it. So we take the lowest limit we have here, x less than 15. And another thing to consider, that height is equals to x. So height cannot equal to 0. X cannot equal to 0. So x should be greater than 0 and less than 15. Make sense?
Yeah.
Yeah.
The way we define the restrictions in this case. You just take a look here at the functions. Is it clear, guys?
Yep.
Self-explanatory.
I already learned it. That's why.
So, okay, then why are we wasting time? What would be the function for volume in this case?
Well, it says it right there. 4x cubed
But
subtract.
why? Can you explain it to me?
This volume is length times width times height.
Exactly.
Whenever you plug it in, you factor it out, and then you simplify it out. You get 4x cubed subtract 180x squared plus 1800x. And then you could solve for x using derivatives.
So again, we need to find the derivative of this function. And derivative of this function would be 12x
Squared.
subtract 12x squared, 360x plus is 1800. Now you solve it for x equal for v of x equals 0, and you're gonna see that you can simplify it by 12. It's gonna be x squared minus 30x plus or actually you maybe can't. 1800 by 12. Yep, so you just treat it as normal quadratic function. You find
1800 divided by 12 is 150.
150, even better. You see everything matches. 150. Now you just need to solve it for x. Once you find those values, you substitute them into the initial function for volume. You define whether it's maximum or minimum of the function. And now you know a perfect ratio of the length, of the width, of the height that gives you the most volume, right, guys?
Mhm.
Yeah.
And you say that you already knew this before?
Yeah, I learned it in
But how? You didn't knew how to
Well-
find the maximum or minimum of the function using the
we
derivative.
learned everywhere up to the point of the to find the volume, and we solved it using a different method, synthetic division. They taught us that way.
So now it's not about just knowing how to solve this type of problems. It's about knowing how to solve them using properties of derivatives, guys.
Yeah.
It's I am not saying that you know from your school is bad. It's just another method. And I'm pretty sure it's much more lengthy than this one.
It is. It's what I meant by it, what I know it do it already is I know the beginning part, and then I could use what I know from derivatives to solve it easier.
So can you see this?
Yeah.
Here is basically a solution that follows the step when you find the,
Oh, they solved it already?
you see it? So here, this is where we stopped. We found the equation for the derivative. We simplified it when it's equals 0. Next step is to solve it, and you're gonna get these two roots.
Do you use quadratic formula?
Here they use the discriminant formula. You know it? x1 and 2 equals minus b plus or minus square root of discriminant
Yeah, so that's
divided by 2a.
we call that the quadratic formula at my school.
Okay, so and you find two roots, and you gotta check first of all, does these two roots are within the range that I'm giving with 0 to 15? And you see right away that 23.7 is not in the range.
Mhm.
This solution does not satisfies the equation.
Mhm.
And you're gonna see that if you substitute 23.7 here, you're gonna have a negative width. That's why. So now 6.3, you substitute it and you find that the optimal volume that you can obtain would be 5,196 cubic meters.
Mhm.
Centimeters, sorry, because you see we're working with centimeters now.
Mhm.
And notice that the endpoints of the domain didn't have to be tested, since it is not impossible. It is impossible to make a box using the value 0 or 15. Well, exactly what I was talking about. We cannot make 0 height or 0 width. Any questions about this?
No.
So in here, the only one that is left is the distance optimization problem, but I'm gonna leave it up for you to discover it. And I'm also gonna post a home assignment for the next Monday.
Okay.
But finish doing a home assignment for unit 3.1, and it was one question from 3.2.
Mhm.
And I'm gonna post 3.2 and 3.3 today.
Okay.
Great job, guys. Thank you for participation. You did a great job today.
Thank you.
Thank you.
Good luck, guys. Have a good night.
You too. Bye.